Hi, I'm Elizabeth with Logic Walk, and welcome to Chapter 5. In this chapter, we'll explore another I/O device, the network device. To see why networks matter, let's start with a simple scenario. Suppose you have photos on your computer that you want to share with a friend. Here's one way you can do that. First, you can save the photos on a portable hard drive, then bring the hard drive to your friend's house. And finally, connect the hard drive to your friend's computer and transfer the photos. If your friend lives close by, this approach, while not ideal, could work. But what if you streamline the process by connecting your computer directly to your friend's, eliminating the need for a portable hard drive? We can treat each computer as an I/O device by cabling them directly, letting them exchange data just as they would a hard drive. This creates a full mesh network where every computer links to every other. That's simple with two computers. But imagine you need to share photos among you, a friend, and two more family members, all of whom must send and receive files with each other. In a full mesh setup for four computers, you'd need six separate cables. Each computer would require three network ports and a dedicated buffer in memory for each of those connections. As you add more machines, the number of cables, ports, and buffers grows exponentially, making direct wiring impractical. We could switch to wireless links to eliminate cables, but then we face new challenges: limited range and signal interference. It's like using walkie talkies. Communication only works when you're in range, and anyone on the same channel can disrupt your connection. To solve these problems, we can use an intermediary device, better known as a network device. Instead of directly connecting computers, we can connect the computers to a network device. In this network setup, all 8 computers connect to a single network device, using just 8 cables instead of the 28 required for a full mesh setup. When one computer sends a message, it includes two things. First, the destination, so the network device knows which computer should receive it, and then a source, so the recipient knows where to send its reply if necessary. The network device reads the destination and forwards the message only to the correct computer. While this simple network is far easier to wire than a full mesh, it has 3 key drawbacks. First, since each computer is only connected to one device, the computer can only send and receive one message at a time. If multiple computers send messages to a single computer at the same time, then the messages will collide, causing delays or failure. Second, the network device is a single point of failure. If that one network device goes down, all computers lose their connections. And finally, this network has limited scalability. Even the largest network devices top out around 100 ports, so you can't hook up hundreds of thousands, let alone billions of computers to a single network device. To overcome these limits, we can add more network devices and link them to other network devices and computers. Computers connect to their nearest network device, and those devices connect to parent network devices, forming a multi-tiered hierarchy. Here, we have a network made up of 5 network devices, ND1 through ND5, and 16 computers, labeled A through P. Together, they form a tree diagram with 21 nodes, and we can grow this tree as large as we need. We can divide these 21 nodes into 3 categories. The root node, which is network device 5, sits at the very top of the hierarchy. It has no parents and is the starting point for every connection below it. Next, we have intermediate nodes, which are network devices 1 through 4. Each descend from ND5. And finally, we have leaf nodes, which are computers A through P. These nodes have no other children and are at the bottom of the hierarchy. If you would like to learn more about nodes, feel free to revisit the data structure course. In this example, if the root node goes down, every child network and its connected computers remain fully operational and can still communicate with each other. For example, if we lost connection with network device 5, computers A through D will still be able to communicate with each other because network device 1 is still operational. With that being said, losing the root node can still be detrimental because all the nodes will lose access to 75% of the network. For example, node M will lose its ability to send messages to nodes A through L. To solve this, we can add one more device, which we'll call ND6, and connect devices 1 through 4 for both network devices 5 and 6. Now, if network device 5 fails, all information reroutes through ND6, keeping all nodes connected. Another benefit to adding network device 6 is that now the traffic that was only flowing through device 5 can now be shared with network device 6, reducing network congestion. To learn more about complex networks, be sure to visit Dijkstra's algorithm, linked in the lesson. That's all for this lesson. In our next lesson, we'll explore how network devices interact with the Logic Walk simulator.